Part 1. Foundations of Space. Space, often imagined as an empty void, is not entirely empty. While it is a near-perfect vacuum, it still contains trace particles of hydrogen, helium, cosmic dust, and high-energy radiation. Even in the most desolate stretches between galaxies, you can find single atoms drifting silently. This emptiness is why sound cannot travel through space. It lacks the molecules needed to carry vibrations. It's a realm where silence is absolute, and light becomes the primary messenger of information. The boundary between Earth and space is known as the Kármán line, positioned approximately 100 kilometers above sea level. While our atmosphere thins gradually, this line is commonly accepted as the threshold of space. Above it, traditional aerodynamic flight is no longer possible, and satellites orbit in graceful arcs around our planet, following the pull of gravity rather than riding on air currents. Light, the fastest thing in the universe, travels at a constant speed of about 299,792 kilometers per second in a vacuum. This unchanging velocity forms the basis of the light year, a measure not of time, but of distance. A single light year spans nearly 6 trillion miles. When you gaze at a star in the night sky, you're not seeing it as it is, but as it was. The light that reaches your eyes tonight may have begun its journey hundreds or even thousands of years ago. Space itself is ancient. The universe, as far as we can observe, began around 13.8 billion years ago in a rapid expansion known as the Big Bang. Contrary to the imagery the name suggests, the Big Bang wasn't an explosion in space, but rather an expansion of space itself. In its earliest moments, the universe was dense, hot, and uniform. Over time, it cooled and allowed matter to form, giving birth to stars, galaxies, and, eventually, the conditions necessary for life. Time behaves differently in space, particularly around objects of great mass. According to Einstein's theory of general relativity, time is affected by gravity. The stronger the gravitational field, the slower time passes. This phenomenon, called time dilation, has been measured using atomic clocks on Earth and in orbit. Near a black hole, where gravity is most extreme, time can slow to a near halt for an outside observer. The deeper you go into space, the stranger and more flexible time becomes. Our solar system is a dynamic and diverse place. It contains 8 primary planets, dozens of dwarf planets, hundreds of moons, and countless asteroids and comets, all orbiting our central star, the Sun. The Sun itself is a massive ball of hydrogen and helium undergoing nuclear fusion. Every second, it converts 600 million tons of hydrogen into helium, releasing vast amounts of energy that sustain life on Earth and drive weather systems, ocean currents, and climate. Mercury, the innermost planet, is a world of extremes. Without a substantial atmosphere to trap heat, its temperatures swing dramatically, from scorching heat during the day to freezing cold at night. Venus, despite being farther from the Sun, is even hotter due to its dense, carbon dioxide-rich atmosphere, which traps heat in a runaway greenhouse effect. The surface of Venus is hot enough to melt lead, and its thick clouds of sulfuric acid make it an inhospitable place. Mars, often called the Red Planet, captivates scientists and the public alike with its dusty surface and hints of ancient water flows. Towering over its terrain is Olympus Mons, the tallest mountain in the solar system, rising nearly 3 times the height of Mount Everest. Although its thin atmosphere makes human habitation difficult, Mars remains a primary candidate for future exploration and potential colonization. Jupiter, the largest planet in our solar system, is a gas giant composed mostly of hydrogen and helium. Its massive size gives it strong gravitational influence, capable of redirecting comets and asteroids that might otherwise threaten Earth. The most famous feature of Jupiter is the Great Red Spot, a swirling storm that has persisted for at least 350 years. This storm is so large that it could easily swallow our entire planet. Saturn, known for its stunning rings, is another gas giant. Its rings are made of countless particles of ice and rock, ranging in size from tiny grains to massive boulders. Despite their immense width, spanning over 280,000 kilometers, the rings are incredibly thin, often no more than 10 meters thick. Saturn's atmosphere features high-speed winds and storms, and it has more than 140 known moons, including Titan, which boasts a thick atmosphere and liquid methane lakes on its surface. Part 2: Moons, Gas Giants, and Deep Space Mysteries. Titan, Saturn's largest moon, is a world shrouded in mystery and atmosphere. It is the only known moon with a dense atmosphere and liquid lakes on its surface, not of water, but of methane and ethane. The skies of Titan are orange and hazy, and its surface pressure is greater than Earth's. Scientists believe that beneath its icy crust, Titan may harbor a subsurface ocean, potentially warmed by tidal forces. This hidden sea could be one of the most promising places in the solar system to search for alien life. Another of Saturn's moons, Enceladus, has surprised scientists with its icy geysers. From fissures in its south pole, nicknamed tiger stripes, jets of water vapor and ice particles shoot into space. These plumes are evidence of a subsurface ocean, and the particles they release contribute to Saturn's E-ring. Enceladus, though only about 500 kilometers in diameter, has become a prime target for astrobiology because of the complex organic molecules detected in its plumes. Moving farther out, Uranus presents one of the strangest rotations in the solar system. It is tilted over 98 degrees, rolling around the Sun on its side. This extreme tilt causes seasons that last over 20 Earth years each. The atmosphere of Uranus is composed mainly of hydrogen, helium, and methane, the latter giving it its pale blue color. Despite its distance from the Sun, Uranus has a faint ring system and at least 27 known moons, many named after characters from Shakespeare and Alexander Pope. Neptune, the outermost known planet, is a deep blue world with powerful storms and supersonic winds. The planet's atmosphere is similar to Uranus in composition, but more dynamic. One of the most notable features observed by the Voyager 2 spacecraft in 1989 was the Great Dark Spot, a storm roughly the size of Earth. Though this storm has since disappeared, new ones continue to form and fade. Neptune's largest moon, Triton, orbits in the opposite direction of Neptune's rotation, suggesting it may have been captured from the Kuiper Belt. The Kuiper Belt itself is a region of icy objects beyond Neptune. It is home to dwarf planets such as Pluto, Haumea, Makemake, and Eris. Pluto, once considered the ninth planet, was reclassified as a dwarf planet in 2006 due to its size and the nature of its orbit. Despite its small size, Pluto has mountains of water ice, thin atmospheric layers of nitrogen and methane, and a massive moon named Charon that is nearly half its size. The two bodies are tidally locked, always showing the same face to each other. Beyond the Kuiper belt lies the hypothetical Oort cloud, a distant shell of icy bodies that may extend nearly halfway to the nearest star. It's believed to be the source of long-period comets, those that take thousands or even millions of years to complete a single orbit around the Sun. Though no object in the Oort cloud has been directly observed, its existence is inferred from the behavior of these ancient comets. Between planets and stars lies the interstellar medium, a mixture of gas, dust, and cosmic rays. While it seems empty, this medium plays a critical role in the formation of new stars and planetary systems. When regions of the interstellar medium become dense enough, they can collapse under gravity, forming a protostar. As the protostar contracts, its core heats up, and eventually, nuclear fusion ignites. A new star is born. Stars themselves have remarkable life cycles. Small stars, like red dwarfs, burn their fuel slowly and can live for trillions of years. Our Sun, a G-type main sequence star, is about halfway through its 10 billion-year lifespan. In roughly 5 billion years, it will expand into a red giant, engulfing the inner planets and shedding its outer layers. The core that remains will become a white dwarf, a dense, slowly cooling stellar remnant roughly the size of Earth. Massive stars live fast and die young. They burn through their hydrogen rapidly and end their lives in supernova explosions. These cataclysmic events create and disperse heavy elements like iron, gold, and uranium into space. The remnants of these explosions can form neutron stars, compact objects with masses greater than the Sun, but only about 20 kilometers in diameter. In some cases, if the remaining mass is sufficient, the core collapses into a black hole. Black holes are among the most mysterious objects in the universe. Defined by their event horizon, the point of no return, they warp space and time in extreme ways. Once something crosses the event horizon, it cannot escape, not even light. At the center of a black hole is the singularity, where gravity becomes infinite, and the laws of physics as we know them break down. Despite their name, black holes aren't voids. They are objects with mass and structure, revealed by their gravitational influence on nearby matter. Surrounding many black holes is an accretion disk, a swirling whirlpool of gas and dust drawn in by gravity. As this material accelerates and heats up, it emits intense radiation, particularly X-rays. This is often how astronomers detect the presence of a black hole. In some cases, jets of high-energy particles are launched from the poles of the accretion disk at near-light speeds, extending for thousands of light-years into space. At the center of nearly every large galaxy, including the Milky Way, lies a supermassive black hole. These giants have masses millions to billions of times that of our Sun. The black hole at the center of the Milky Way, known as Sagittarius A star, has a mass of about 4 million suns. Though invisible directly, its existence is confirmed by the orbits of nearby stars and the radio waves it emits. Part 3. Light, Time, and the Scale of the Universe. Light, though weightless and without mass, is the key to understanding the universe. It travels through space at a constant speed, nearly 300,000 kilometers per second, and it brings us all the information we have about the cosmos. Because nothing can travel faster than light, it acts as a kind of cosmic clock. When we observe distant galaxies, we are seeing them as they were in the past, not as they are now. The farther away an object is, the older the light that reaches us. A galaxy 1 billion light-years away appears to us as it was 1 billion years ago. This means that every night sky is a kind of time machine, allowing us to peer into ancient epochs. The cosmic microwave background, the oldest light in the universe, was released just 380,000 years after the Big Bang. It permeates all of space and represents the cooled remnants of that original expansion. Detected in every direction, it forms a uniform, faint glow that helped confirm the universe's explosive origins. The vast distances between celestial bodies are hard to grasp. The Sun is about 150 million kilometers from Earth. Light from the Sun takes about 8 minutes to reach us. That same light would take over 4 years to reach the nearest star system, Alpha Centauri. The Milky Way galaxy itself is about 100,000 light-years across, and even then, it's just one among hundreds of billions of galaxies in the observable universe. Each galaxy contains billions or even trillions of stars, and most of those stars likely host planets. This means the number of potential worlds in the universe is almost incomprehensible. According to some estimates, the observable universe contains over 1 septillion stars. That's a 1 followed by 24 zeros. If even a small fraction of these stars host habitable planets, the potential for life elsewhere is enormous. Gravitational lensing is a fascinating consequence of Einstein's theory of general relativity. It occurs when a massive object, like a galaxy cluster, bends the light coming from a more distant object. This can magnify, distort, or duplicate the appearance of the background source. Through gravitational lensing, astronomers have been able to observe galaxies that would otherwise be too faint or distant to detect, giving us deeper glimpses into the early universe. Another phenomenon, redshift, also reveals the universe's expansion. As light travels through expanding space, its wavelength is stretched, moving it toward the red end of the spectrum. The more distant a galaxy is, the more its light is redshifted. This discovery, first made by Edwin Hubble in the 1920s, led to the understanding that the universe is not static, but constantly growing. Even now, galaxies are moving away from each other, and the space between them continues to expand. This expansion is driven by a mysterious force known as dark energy. While it cannot be seen or measured directly, its effects are unmistakable. Dark energy appears to make up about 68% of the total energy in the universe, counteracting gravity and accelerating cosmic expansion. Its true nature remains one of the greatest mysteries in modern astrophysics. Dark matter, another invisible substance, accounts for roughly 27% of the universe. Unlike dark energy, dark matter exerts gravitational force but emits no light or radiation. It does not interact with electromagnetic forces, making it invisible to our instruments. However, its presence is inferred through the movement of galaxies and the way they rotate. Without dark matter, galaxies would not have enough visible mass to hold themselves together. The remaining 5% of the universe is what we call normal matter, the atoms and molecules that make up stars, planets, people, and everything we can see. It's humbling to realize that everything we have ever observed, touched, or understood makes up only a tiny fraction of the universe's total composition. Even within our small corner of the universe, we are constantly learning. The Sun, though familiar, is a dynamic and powerful object. It generates solar wind, a stream of charged particles that flows outward through the solar system. This wind shapes planetary magnetospheres and creates auroras when it interacts with Earth's magnetic field. During solar storms, bursts of particles and radiation can disrupt satellites, power grids, and even GPS systems on Earth. The heliosphere is a vast bubble carved out by the solar wind, extending far beyond Pluto. It shields the solar system from a significant portion of galactic cosmic radiation. At its edge lies the heliopause, the boundary where the solar wind slows and merges with the interstellar medium. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Voyager 1, along with its twin Voyager 2, was launched in 1977. These spacecraft have traveled farther than any other human creation. On board each is a golden record, a time capsule containing images, sounds, and music from Earth, intended for any intelligent life that might find it. Among the recordings are greetings in dozens of languages, the sound of a baby crying, and music from Beethoven, Bach, and Chuck Berry. Another spacecraft, New Horizons, provided the first close-up images of Pluto in 2015. What was once a blurry dot became a rich, detailed world with icy plains, mountains of frozen nitrogen, and a hazy atmosphere. New Horizons continues to explore the Kuiper Belt, sending back data from billions of kilometers away. Even closer to home, the International Space Station orbits Earth at an altitude of about 400 kilometers. It completes a full orbit every 90 minutes and is visible from the ground at dawn or dusk. The station serves as a laboratory for studying life in microgravity, advancing research in biology, physics, and materials science. It's a testament to international cooperation, housing astronauts from around the world. Part 4. The Lives of Stars and Cosmic Structures. Stars begin their lives in massive clouds of dust and gas known as nebulae. Within these cosmic nurseries, regions of gas become denser over time due to gravity, forming clumps that collapse and heat up. As the temperature and pressure at the core of these protostars increase, nuclear fusion ignites, marking the star's official birth. The star enters a stable phase known as the main sequence, where it spends most of its life fusing hydrogen into helium in a delicate balance between outward pressure from fusion and inward pull from gravity. A star like our Sun will remain in the main sequence phase for about 10 billion years. As it runs out of hydrogen fuel, the balance breaks. The core contracts, heating the outer layers and causing them to expand. The star becomes a red giant. In the case of the Sun, it will eventually shed its outer layers in a gentle, glowing shell called a planetary nebula, leaving behind a white dwarf, an Earth-sized remnant of degenerate matter that cools slowly over billions of years. Larger stars live much shorter, more dramatic lives. After burning through their fuel, these stars collapse rapidly, triggering a supernova explosion. The outer layers are ejected into space, enriching the surrounding interstellar medium with heavy elements. These elements, iron, gold, uranium, are created only in the extreme environments of stellar cores and supernovae. The remnants of these massive stars may become neutron stars or, if enough mass remains, collapse into black holes. Neutron stars are among the densest objects in the universe. A single teaspoon of neutron star matter would weigh billions of tons. These stars can rotate at incredible speeds, sometimes hundreds of times per second, emitting beams of radiation that sweep across space. These objects are called pulsars, and their precise pulses make them cosmic lighthouses that can be used to measure distances and even test the laws of physics under extreme conditions. Some neutron stars become magnetars, stars with magnetic fields so strong that they can distort atomic structures and trigger massive starquakes. These quakes release intense bursts of X-rays and gamma rays that can be detected across galaxies. Though rare, magnatars offer insights into matter at its most extreme, and remain one of the most fascinating endpoints of stellar evolution. Beyond individual stars, space is filled with vast structures shaped by gravity and time. Galaxy clusters are collections of hundreds or thousands of galaxies, bound together by their mutual gravitational pull. These clusters often contain large amounts of hot gas that emit X-rays, visible to telescopes designed to observe high-energy light. Within these clusters, dark matter acts like an invisible web, influencing the motion of galaxies and the shape of the cluster itself. Superclusters are even larger formations, made up of multiple galaxy clusters linked together by vast filaments. Our Milky Way is part of the Local Group, which belongs to the Laniakea supercluster, a structure that spans over 500 million light-years and contains more than 100,000 galaxies. These grand designs form the cosmic web, a network of filaments and voids that stretch across the observable universe. Despite the scale of these structures, the universe appears remarkably uniform when viewed on the largest scales. This uniformity is a key prediction of the Big Bang model, and has been confirmed by observations of the cosmic microwave background. Small fluctuations in this background radiation helped seed the formation of galaxies and clusters, shaping the large-scale structure we observe today. One of the most powerful tools astronomers use to study the universe is spectroscopy. By analyzing the light from stars and galaxies, scientists can determine their composition, temperature, motion, and even age. Each element absorbs light at specific wavelengths, creating a unique spectral fingerprint. These fingerprints reveal not just what stars are made of, but how fast they are moving toward or away from us through the Doppler effect. When an object in space moves away from us, its light is stretched into longer wavelengths, causing a redshift. If it moves closer, its light is compressed, resulting in a blue shift. These shifts allow astronomers to measure the expansion of the universe and detect planets around distant stars by observing the subtle wobbles they cause in their host star's motion. Exoplanet detection has become one of the most exciting frontiers in astronomy. Thousands of planets have been discovered orbiting stars beyond our solar system, many of them using the transit method. This technique involves measuring the tiny dip in a star's brightness as a planet crosses in front of it. By studying these transits, scientists can determine the planet's size, orbit, and even atmospheric composition if starlight passes through its atmosphere. Some of these exoplanets lie within their star's habitable zone, the range of distances where liquid water could potentially exist. One of the most promising systems is TRAPPIST-1, which contains 7 Earth-sized planets, 3 of which are in the habitable zone. Another, Kepler 452b, is considered a potential Earth twin, though it orbits a star much older than the Sun. The diversity of these planetary systems suggests that the conditions for life may be common in the galaxy. With the launch of the James Webb Space Telescope, astronomers now have the ability to study exoplanet atmospheres in unprecedented detail. Webb can detect biosignatures, chemical clues like oxygen, methane, and carbon dioxide that may indicate biological processes. While we have yet to find definitive evidence of life beyond Earth, the search continues with growing precision and enthusiasm. The potential for life elsewhere extends beyond planets. Moons like Europa and Enceladus, with their subsurface oceans, may host microbial ecosystems in the darkness beneath their icy shells. On Titan, complex organic chemistry takes place in lakes of liquid methane and ethane. These environments challenge our understanding of habitability and broaden the scope of our search for life in the cosmos. Part 5. Wonders Beyond and the Future of Exploration. One of the most visually stunning features in the cosmos is the nebula. These vast clouds of gas and dust come in many types, including emission nebulae, reflection nebulae, and planetary nebulae. Emission nebulae glow brightly due to high-energy radiation from nearby stars, which ionize the gas and cause it to shine. The famous Orion Nebula is a prime example, an active stellar nursery where new stars are forming even now. Reflection nebulae, on the other hand, do not emit light on their own, but instead reflect the light of nearby stars, often appearing as soft, bluish clouds. Planetary nebulae, despite the name, have nothing to do with planets. They are the final exhalations of dying stars like the Sun, forming delicate, colorful shells of gas that slowly disperse into the interstellar medium. Another celestial phenomenon that captivates astronomers is the quasar. Quasars are the bright, energetic centers of distant galaxies, powered by supermassive black holes consuming vast amounts of matter. As this matter falls into the black hole's accretion disk, it is compressed and heated to extreme temperatures, releasing tremendous energy. Some quasars outshine entire galaxies, despite their light traveling billions of years to reach us. Observing quasars allows astronomers to study the early universe, as most are located extremely far from Earth, representing a time when the universe was still young. Gamma-ray bursts are among the most energetic explosions ever observed. Lasting from a few milliseconds to several minutes, they release more energy in that brief moment than the Sun will produce over its entire 10 billion-year lifetime. These bursts are believed to be caused by either the collapse of massive stars into black holes or the merger of neutron stars. Their power is such that if one occurred close enough to Earth, it could potentially strip away our atmosphere. Thankfully, these events are extremely rare and typically occur billions of light years away. Cosmic rays are another mysterious feature of the universe. These are high-energy particles, mostly protons, that travel through space at nearly the speed of light. Some originate from the Sun, while others come from distant galaxies or supernova explosions. When these rays collide with Earth's atmosphere, they produce showers of secondary particles. Scientists continue to study cosmic rays to better understand the processes that accelerate particles to such extreme energies and how they affect both space weather and technology. Space is not only a place of beautiful phenomena, but also one of intense extremes. The Boötes void, for instance, is a massive region of space with very few galaxies. Essentially, a supervoid stretching nearly 330 million light-years across. Its emptiness challenges our understanding of how galaxies are distributed and raises questions about the nature of cosmic structure. On the other end of the spectrum are dense star clusters like globular clusters, which contain hundreds of thousands of stars packed into a sphere only a few dozen light-years across. These clusters orbit the outskirts of galaxies and represent some of the oldest known stellar populations. Time in the universe stretches far beyond human imagination. The current age of the universe, 13.8 billion years, is only the beginning of what lies ahead. Stars like our Sun will fade. Galaxies will drift farther apart as space continues to expand. Over unimaginable timescales, white dwarfs will cool into black dwarfs. Black holes will slowly evaporate via Hawking radiation, and even subatomic particles may decay. This long, cold future is sometimes called the heat death of the universe, a distant state of maximum entropy where no usable energy remains. Despite this, the present era is one of extraordinary beauty and discovery. Humanity is only at the dawn of its journey into space. Robotic explorers are mapping distant worlds. Telescopes like James Webb and its successors will peer into the atmospheres of exoplanets and the faintest corners of the cosmos. Missions to Mars are underway, with plans to send humans there in the coming decades. Private companies and international collaborations are making space travel more accessible than ever before. The dream of interstellar travel, journeying beyond our solar system, remains distant but not impossible. Concepts such as light sails, nuclear fusion drives, and even hypothetical warp drives are being studied. While the barriers are immense, so too is the human desire to explore, to reach beyond the limits of the known, and to find our place among the stars. Back on Earth, when we look up at the night sky, we see more than dots of light. We see stories, distances, and moments from the past. Every photon that reaches us is a message from another place and time. The universe is not just out there, it is part of us. The atoms in our bodies were forged in stars that lived and died long before Earth was born. We are, quite literally, made of stardust. This truth connects us to everything we see in the sky. From the moon's quiet pull on the tides to the swirling dance of galaxies across the cosmos, we are part of the universe's ongoing story. And while space is vast and silent, our understanding of it is growing with every passing year. So, as you rest, let this final thought settle gently in your mind. The universe is filled with light, mystery, and wonder. And you, simply by being here, are woven into the very fabric of it.